So in the previous video we were seeing the multiplication of even and odd functions. The even function we saw that completes the property of f of x is equal to f of minus x, and also the integral from, let me say, minus L to L of f of x dx is equal to 2 times the integral from minus L to L. So sorry, from 0 to L of f of x dx. But you can also put it L, a minus L, a plus L, a to L. The next issue was for a odd function. For a odd function, we have that f of minus x. I think you see better here. F of minus x is equal to f of minus f of x, and also now the defined integral from minus L to L of f of x dx is 0. In the previous video we proved that the even function times a even function is a even function. Now on this video we will see that the odd function times a odd function is a even function, and later that the odd function times a even function, or vice versa, is a odd function. So we have f of minus x, and this needs to be equals at the end f of x in order to have a even function. I'm doing this proof. So f of x or f of minus x, I'm talking about this result function is f. This resultant function needs to accomplish these two. Now let me see this property. So I have a odd function times another odd function. Alright, so I have f of minus x. If my functions are phi and c, also I would have phi of minus x times c of minus x. But because these are odd functions, they complete this property. Which property? This property. So I can put them as minus phi of x times minus c of x. This is equal to phi of x times c of x, and this is equal to f of x. Or you can do it the other way around. You can, f of x is equal to this. I can add a negative sign, so multiply by negative 1, and it's the same thing. So we also prove this one. A odd function times a odd function is a even function, and lastly, a even function times a odd function. So now I have f of minus x, and this is a even function and a odd function. So phi would be my even function, and c would be my odd function. So this, because it's even, I can put it as phi of x, and this, because it's odd, I can put it as a negative c of minus x. This is equal just to negative psi of x. This is equal just to negative phi of x times c of x, and this is the same as negative. This is f of x, and so I have that f of minus x is equal to minus, or to, sorry, f of, sorry, I'm saying it in English terms and not in mathematical terms. F of negative x is negative f of x, and so we prove this the function, the property that a odd function times a even function, or vice versa is a odd function. Now, why is this important for Fourier series? Because let me erase. Oh, here it is. Because remember that the Fourier coefficients are a sub n, or here, a sub n is equal to 1 over pi times the defined integral from minus pi to pi of f of x cosine of nx dx. B sub n is equal to 1 over pi times the defined integral from minus pi to pi of f of x sine of nx dx. So if, and well, the constant c sub 0 is equal to a sub 0 over 2, that is 1 over 2 pi times the defined integral from minus pi to pi of f of x. Alright, so now please not too much light. Perfect. So if f of x is a even function, so if I have f of x is a even function, so I have here a even function times a even function is a even function. So this is a even function. So I have a sub n is whatever this times a defined integral from minus L to L of a even function, and this would be equal to then a sub n. So for an even function, I have not much space. So for an even function, I would have that the Fourier a sub n coefficient would be 1 over pi times 2 of the defined integral from 0 to pi of this even function, whatever even function it be. For b sub n, I have a even function times a odd function. So this is a odd function, and the defined integral, erase it. The defined integral from minus L to L of f of x, when f of x is a odd function, is equal to 0. So b sub n would be equal to 0. C sub 0 would be, here I just have the defined integral of a even function, so here I just have this is a even function, and so I can put it as 2 times this, so I will just have, this is 1 over pi times the defined integral from minus pi, so sorry, times the defined integral from 0 to pi of f of x dx, and a sub 0 is just 2 over pi times the defined integral from 0 to pi of f of x dx. So for an even function, you already know that the coefficients on the Fourier series would be just a sub n would be this, the c sub 0 would be this, and you would have no terms with b sub n. And so you would have no terms at the end with sign. Maybe when you do the integral here, you have some sign terms, that would be the other thing. Yeah. Now for a odd function, we would have a odd function times a even function is a odd function, and the defined integral from minus pi to pi of a odd function is 0. So a sub n would be 0. B sub n, the a odd function times a odd function is a even function. The defined integral from minus pi to pi of an even function would be 2 over pi times the defined integral from 0 to pi of whatever odd function, whatever even function I have now. And here the defined integral from minus pi to pi of a odd function is just 0. So for a even function, on the Fourier series, I have that f of x could be approximately equal to a sub 0, c sub 0 plus the summation from n equals 1 to infinity of the coefficients that I used a sub n, that is just this stuff, a sub n times cosine n x. And for a odd function, I would just have that f of x is approximately equal to just the infinity summation from n equals 1 to infinity of b sub n sine of nx. So now, on the next videos, we will do examples of this. We actually will take a function f of x equals x, f of x equals x, square x, and we will do the Fourier series on that. We will calculate the coefficients and then the Fourier series, and it will be an amazing thing.